So let's start with the first step. Let's show that being immutable will imply that you can find some unit vector with finite support on the L2 of G that's kind of not getting moved around by your left regular representation. Okay, so that's one implies two. So suppose G is immutable. Okay, and we're actually going to use the characterization from the Fulner's condition. So there exists a Fulner's net. Okay, the Fulner's net. Basically, if you recall, what it means is that let's call it their F alpha, they're finite subsets of G, so that for every S inside G, if you consider the shift of these F alpha by S, you take the set difference with alpha, see how far it gets shift by these S, and it's not going to be too much, okay? So the proportion-wise, that's going to go to zero, okay? So that's the Fulner's condition. So that's, well, your G here is discrete. So what you can do is that you can build a unit vector that's kind of supported on these F alpha. And you see these, because these F alpha doesn't get a shift by your left regular representation or left translation too much. So when you take the left regular representation on some function defined on these F alpha, then it won't be shift too much as well. Okay, so how you build a unit vector is kind of easy. You take a so let's say psi of alpha to be, you take the characteristic function of the F alpha, okay? So that's going to, well, it's not going to be a unit vector. So you take is divided by its length, which is, you consider its L2 norm is basically how many elements you take the square root of that. So you divide it, okay? You divide by the number of elements to the half power. Okay, so this is going to be sitting inside the L2 of G. Everything is discrete. So you can clearly see why this is in the L2. Here your F alpha is finite. Okay. So what you can do is that, well, if you consider the left translation of these psi alpha, so let's say lambda s, left translate, so minus psi alpha, okay? So what it does is essentially just evaluates its two norm. So it's, well, let's take the square. So for every t inside G, you consider what's the value of the psi alpha of the left translation, so S inverse t. Take the difference with the psi alpha of t, the whole thing squared, all right? And let's just think about what happens when you evaluate these psi alpha. Well, first of all, let's just write down the definition. So this is essentially just summation t inside G. All the psi alpha, you have a constant of f alpha to the half, and you take the square. So let's move that out. So that's 1 over f alpha, and take it out of summation. And this is essentially the characteristic function of f alpha with S inverse t, and you minus the characteristic function f alpha evaluate at t, the whole thing squared. And what is the first one? Well, it's kind of trivial now. We kind of done this calculation before. So this one is either 1 or 0. So it's 1 if this S inverse of t is inside f alpha. But that's actually if and only if your t, so t is the variable, S is fixed. So t is in the last translation of your f alpha. Okay, so 0 if t is not in the S of f alpha. So this is essentially the characteristic function of the left translation by S of this f alpha. All right, evaluate t, of course. All right, so this one you can write it as 1 over f alpha, and you compare the difference of two characteristic functions. So S of f alpha, evaluate t, minus the characteristic function of f alpha, evaluate t. And basically now we use the same argument from last time. So you take the difference of two characteristic functions, you take their normal square. The only time this is non-zero is that your t is in exactly one of them, either in SF alpha or in F alpha, but not in both or not in none of them. All right, so this is essentially just counting how many elements are there that's in exactly one of the F alpha and its translation. So this is basically the SF alpha set difference with F alpha, and you divide this whole thing by F alpha. And because you have a fullness condition, these are going to go to 0. So basically, that just shows the psi alpha, this vector, this unit vector, will satisfy this condition. Okay, satisfy the condition 2. All right, so now let's show how you can build from condition 2 to a bunch of positive definite function and satisfy some conditions. So let's say 2 implies 3. So what you do is that let's first of all, if you give you a vector psi inside the L2 of G, I can always build a positive definite function by the following. So I can define a map, let's say phi of psi, evaluate G to be is essentially just do the left regular representation, shift my vector, and then I inner product this vector. Okay, so in fact, all the positive definition function come in this way, using some representation. So here we're only using the left regular ones. First of all, let's claim that this is going to be positive definite. Okay, so I want to claim that this phi of the psi is a positive definite. All right, why is that? Well, first of all, from your assignment, you already see that because your lambda is a unitary representation. So if you take any, say, G1 up to Gn, because your lambda is a unitary representation, it's going to be an operator-valued positive definite function. That's what I call it on your assignment. So if you construct this operator matrix, let's say lambda evaluate at Gi inverse Gj, this operator matrix is going to be positive. And if you really think about what happens, if you want to show this phi psi of G is still positive definite, what you want is that I want you replace each of these entry by this inner product. Okay, so you basically want the inner product of your matrix Gi inverse Gj. You take on vector and you inner product with this vector. You want that to be positive definite matrix as well. Okay. Well, let's just prove a more general fact. So let's prove a little lemma. So let's assume that I have some operator matrix, let's say Aij, inside, say, n by n operator matrix, B of H, and that's going to be a positive matrix, okay? And so let's say for every psi inside this H, I claim that you replace each of these Aij by Aij, you take on the psi, and then you inner product with psi. Basically, that's become a n by n scalar value matrix. That's still going to be a positive definite matrix, okay? Well, why is that? Well, it's pretty much obvious. Let's just prove this little lemma. So if you want to show something that's positive definite, you just need to show that if you test it on any vector, then that's going to be positive definite, or in other words, this matrix, Aij, psi, is positive definite. That's even only if for every C1 up to Cn, so you take on a C1 up to Cn scalar n-dimensional vector, you take on this vector in the product with the vector. If you return a non-negative value always, then your matrix is positive definite. So if you write it out, that's essentially just saying if you take the double summation of I going from 1 to n, j also going from 1 to n of your ij entry, aij psi with psi, and then what you take is that you take on the cj, all right, and you take on a ci bar, okay, that's going to be positive, okay, so that's essentially what it does. But you can move these ci, cj inside this inner product, okay, so that's what you need. This double summation is you move the ci, cj using the inner product is linear in the first coordinate and conjugate linear in the second. So you rewrite it this way. You rewrite it as the aij of the cj psi inner product with the ci psi. Okay, that's positive. Well, this one, essentially, this is what you can do is that you take the operator matrix and you evaluate on the cy psi up to cn psi. So these are basically n copies of H, okay, n of these vectors. and you inner product with the same thing. Okay, so Cn of psi. This is essentially what it does. Okay, and because your Aij, this operator matrix positive, so when you test it on this particular vector, that's going to be positive. Okay, so so that just shows that when you drop it to the Aij side with psi, then it's still positive. Okay, so everything is positive. Now let's finish the proof. Okay, so what we have is that this phi psi is indeed a positive definite function. All right, so now let's assume 2, and let's try to build some positive nice in the positive definite function. So let's let these psi alpha to be the unit vectors in vectors in the part 2. Okay, so they're finite support and they're unit vectors, and the left regular representation doesn't shift them too much. Okay. So let's let these phi alpha to be how you construct. So we already saw how you construct from a unit vector, okay, or any vector. So let's just let phi alpha to be phi of the psi alpha. Essentially, you take the left regular representation, map it, shift your vector, and you take the inner product with your vector, okay. So we already see that this is positive definite, okay, that's no problem. And because they're unit vectors, so if I evaluate at the identity, so this is the lambda b tested on the psi alpha, but at identity, this is basically the identity operator. So this is the inner product with the psi alpha with itself, which is the length of psi alpha, which is 1, okay, because they're unit vectors. Okay, so your these positive definite functions satisfies they're equals to 1 at the identity. And finally, if you have for every s inside the G, because your lambda s psi alpha is converging to the psi alpha in the L2 norm, okay, or you take the difference, that's going to be 0 at the L2 norm. So basically, what you can see is that, so this is in the L2, so phi alpha E, if you take its value, okay, so that's going to basically sorry, not E, but S. So this is lambda S psi alpha with a psi alpha. But this one will get arbitrarily close to psi alpha. And again, the psi alpha is a unit vector, so psi alpha, their inner product is 1. So this one is going to converge to 1, okay, as alpha gets large. All right, so basically now we have a pointwise convergence to 1. And finally, if you want to see whether this is finite support, you just think about phi alpha of S. Basically, that's equals to the lambda S psi alpha with psi alpha. But this is really the inner product in the L2 space. So what you can do is that you essentially just say, well, let's take a summation. Well, T is inside G. What you do is you evaluate psi alpha at S inverse T, and then you product with the psi alpha with T but conjugate. And because your psi alpha has finite support and you want to shift it, if you shift it too much, of course, then you get something that's one of them has to be 0. So this one is non-zero if there exists some T, so that these S inverse T and T, they're both in the support of the psi alpha. And you see, because the support of psi alpha is finite, there are not many S satisfy this. Okay, so basically you have the support of the phi alpha is also finite. Okay, so this way we build a bunch of positive definite functions that converge pointwise to 1, and they're both also finite support. Okay, so let's finish the proof of 2 implies 3.